Okay, these are notes for 4.3, 4.4a. This lesson is over the first fundamental theorem of calculus, and we're also going to look at position, velocity, acceleration concepts. So first fundamental theorem of calculus, I'm going to abbreviate using FFTC. Okay. So the idea here is we can find the area of a region, exact area under the region, rather than using limit definition. We can use our integral many times when we first start off using power rule, integral power rule to find the area of the exact area of a region, kind of a shortcut method. Okay, so the first theorem of calculus says that the definite integral of f of x from a to b is equal to uppercase f of b minus uppercase f of a, where uppercase f is the antiderivative of f. So once we find the integral of little f of x, which we're representing using uppercase f of x, then we just plug the upper and lower bounds into our antiderivative to essentially find the area of a region between the curve and the x-axis. Okay. We'll talk a little bit about that. It may not necessarily give you the area because we do have positive and negative portions. Okay. Now let's recall a couple of concepts that we studied in first from first semester, and it's that the general derivative, a function's general derivative, is essentially a slope-finding function. Right. So if I find a derivative and I end up with 2x plus 1, then this 2x plus 1 can be used to find the exact steepness at any point, any x value I give it, okay, on the graph. Okay. The specific derivative, or a number that, if we find a specific derivative, we're going to come across a number, is the actual slope at a point. So if I'm looking at a specific curve and I want to find the exact steepness on that curve, I can plug 3 into my derivative, my slope finding function, and it'll tell me the exact steepness on that point on the curve. Okay. Likewise, the indefinite integral is an area finding function. So derivative, we're essentially concerned about finding slope, and indefinite integral, we're essentially concerned about finding area. So just like how general derivative is a slope finding function, the indefinite integral is an area finding function. Okay. Specific derivative is the actual slope at a point. The definite integral is the actual area of a region for an interval. Okay, so we do see some similarities between a general and specific derivative, as well as indefinite and definite interval. All right. If a function is continuous on a closed interval, okay, no breaks in the graph, and the endpoints are defined, then the function is able to be integrated on that interval. Okay, so we're able to find the area of a region as long as it's continuous and it's on a closed interval. Notice that there's nothing here about the function having to be differentiable. So we can have a region with sharp points and we can still find the exact area of that region. Okay, however, if we want to find the slope, we have to make sure that our function is differentiable. However, that is not going to be the case if we're trying to integrate or trying to find the area of a closed region. Just have to make sure it's continuous. Okay. All right, let's look at some examples. Evaluate the definite integral of our function 3x squared plus 4x minus 1 from 1 to 4. So here's our lower bound, here's our upper bound. We are going to, the first few steps the first steps will look exactly the same as finding an indefinite integral. So we go through power rule. This is set up for us to apply power rule. No need to expand or rewrite our function. So we go through power rule. 3x cubed over 3 plus 4x squared over 2 minus x. Okay. So we're trying to find the area of this region, under this curve between 1 and 4. So the next step is we're going to evaluate using our upper and lower bounds. Okay, so the notation here is a half bracket on the right with upper bound up top and lower bound 1 seen here. Okay, we're essentially going to be applying the first fundamental theorem of calculus, where after we find the indefinite integral, we're now going to plug the upper bound in to our function, and then we're going to do minus, then we're going to plug our lower bound into the function. So it'll look like this. Okay, so first we plug the upper bound. Upper bound 4 gets plugged in for every x that you see. Okay, so we get 4 cubed plus 2 times 4 squared minus 4. So all this represents f of a. Sorry, f of b. Okay, minus. Okay, make sure that this minus is always here. Okay, always part of your first theorem of calculus. And then plug the lower bound into the equation that you just plugged in for 4. Okay, so 1 gets plugged in for all the x, so 1 cubed plus 2 times 1 squared minus 1. So all this represents f of a. Okay, so we evaluate and we get 92. All this comes out to be 92. All this comes out to be 2. So 92 minus 2 is 90. So the definite integral from 1 to 4 for of the region under the curve will be 90. Okay. One note here is no need to worry about plus c. It will just naturally cancel out. So when we're dealing with definite integrals, we're finding the area of a region, we don't have to worry about the plus c. We only have to worry about plus c if we're trying to find the indefinite integral and coming across, resulting with the area finding function. Okay. Let's look at number 2. Evaluate the definite integral of 2x from -2 to 1. So first step is the same as in finding indefinite integral. Find the go through power rule. So 2x squared over 2, which reduces to be x squared. And now we're going to evaluate between our lower and upper bound. Plug the upper bound first, so we get 1 squared, minus, now we plug the lower bound in, -2 quantity squared. So again, this portion represents f of a, minus, and then this portion represents f of b here, followed by f of a. Okay. And we get 1 minus 4, which is -3. Now, -3 is not necessarily, it's not going to be the area, because what happens is that anytime you have portions of the graph below the x-axis, that's going to result in a negative value. So if you have portions of the graph that is above the x-axis and another portion that is below the x-axis, we're going to have to find the integral separately if we want to find the area of all those regions between the curve and the x-axis. So we've got to keep in mind that any portion that sits below the x-axis is going to produce a value, a negative value. Okay. So sometimes we may have to adjust the negative if we want to find the area for that region. Okay.